Hello there, and welcome to Cosmic Sleep Stories. I'm so glad you found your way here tonight. Maybe you've always been fascinated by black holes, those mysterious cosmic objects where gravity becomes so strong that not even light can escape. Or perhaps you're simply seeking a quiet place to rest your mind. Either way, you're exactly where you need to be. You can rest now. Tonight, you have nothing to do but let go. Let your breathing slow, steady as the event horizon of a black hole, that invisible boundary beyond which nothing returns. Let your body relax, sinking into comfort like matter falling toward a singularity, pulled by gravity into a state of complete rest. Let your mind drift into the darkness, that same darkness that fills the universe between the stars, punctuated by these strange objects that have captured human imagination since we first understood they exist. Over the next hour and more, we'll explore together 150 gentle truths about black holes. We'll discover what they really are, how they form, how they behave. We'll separate myths from reality, fiction from science. We'll visit the supermassive black holes at the centers of galaxies and the stellar mass black holes scattered throughout space. We'll contemplate what happens at the event horizon, what it might be like to fall into a black hole, and what these strange objects tell us about the nature of space, time, and reality itself. Some facts will captivate you. Others will simply wash over you like gravitational waves rippling through space-time, leaving only soft impressions as you drift towards sleep. And that's perfectly fine. There's no need to remember every detail. Just let yourself be carried by the wonder of these cosmic mysteries, by the strange beauty of objects so extreme they bend space and time around themselves. Black holes aren't the terrifying monsters of science fiction. They're natural objects, governed by the same laws of physics that govern everything else in the universe. They're strange, yes, and extreme, but also peaceful in their way, quietly existing in the depths of space, following the rules that Einstein discovered over a century ago. And before we begin our journey into the darkness, if these quiet cosmic explorations help you unwind at the end of your day, consider subscribing to Cosmic Sleep Stories. It helps others find this peaceful corner of the universe, one sleepy soul at a time. Now, close your eyes if you'd like. Breathe slowly, feeling yourself held by Earth's gravity, that same fundamental force that creates black holes when it becomes strong enough. And let's begin our journey into the heart of darkness, into the strangest objects in the cosmos. Fact 1. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from inside a certain boundary. This boundary is called the event horizon, and it's the defining feature of a black hole. Fact 2. Black holes aren't actually holes. They're objects, extremely dense concentrations of mass compressed into incredibly small volumes. The hole part is a metaphor because things fall in but don't come back out, like falling into a hole in the ground. Fact 3. The term black hole was coined by physicist John Wheeler in 1967, but the concept is much older. The idea that gravity could be strong enough to trap light dates back to the 1780s, when scientists first understood that light might be affected by gravity. Fact 4. Black holes are predictions of Einstein's general theory of relativity, published in 1915. Einstein showed that massive objects curve space-time, and if you compress enough mass into a small enough space, the curvature becomes so extreme that it creates a black hole. Fact 5. Ironically, Einstein himself didn't believe black holes actually existed. He thought they were mathematical curiosities, solutions to his equations that nature would somehow avoid. He was wrong. Black holes are real, and we've now observed many of them. Fact 6. The first person to work out the mathematics of black holes was Karl Schwarzschild, a German physicist serving in World War I. While stationed on the Russian front in 1915, he solved Einstein's equations and found what we now call the Schwarzschild solution, describing a non-rotating black hole. Fact 7. Schwarzschild did this work while suffering from a painful autoimmune disease. He sent his solution to Einstein, who was amazed. Sadly, Schwarzschild died just a few months later, never knowing how important his discovery would become. Fact 8. The event horizon of a black hole is not a physical surface. It's an imaginary boundary in space. If you were falling toward a black hole, you wouldn't notice anything special as you crossed the event horizon. No barrier, no warning. You just keep falling. Fact 9. The size of a black hole's event horizon depends on its mass. More massive black holes have larger event horizons. The relationship is simple. The radius of the event horizon, called the Schwarzschild radius, is proportional to the mass. Fact 10. If you could compress the Earth into a black hole, its event horizon would have a radius of about 9 millimeters. The entire mass of the Earth squeezed into a sphere smaller than a marble. Of course, this is impossible with any known physics, but it illustrates how dense black holes are. Fact 11. If you compress the Sun into a black hole, its event horizon would have a radius of about 3 kilometers. All of the Sun's mass, enough to hold 1,000,000 Earths, compressed into something the size of a small town. Fact 12. The density required to create a black hole decreases as the mass increases. A black hole with the mass of the Sun would be incredibly dense. A black hole with 1,000,000,000 times the Sun's mass would have a much lower average density, possibly even lower than water. Fact 13. This seems paradoxical, but makes sense when you understand that the event horizon grows faster than the volume inside it as you add mass. Supermassive black holes, despite containing billions of solar masses, can have average densities similar to air. Fact 14. At the center of every black hole, according to general relativity, lies a singularity, a point of infinite density where all the black hole's mass is concentrated. This is where our physics breaks down, where the equations give nonsensical answers. Fact 15. The singularity is hidden inside the event horizon, protected by what physicist Roger Penrose called cosmic censorship. Nature, it seems, doesn't allow naked singularities visible from the outside. All singularities are clothed in event horizons. Fact 16. We don't really know what happens at the singularity. Our current theories of gravity and quantum mechanics both apply at that scale, but give contradictory answers. We need a theory of quantum gravity to truly understand what's at the center of a black hole. Fact 17. Some physicists think singularities don't actually exist, that quantum effects prevent matter from being compressed to infinite density. The true center of a black hole might be something else entirely, something we can't yet describe mathematically. Fact 18. Black holes can rotate, and most probably do. A rotating black hole is called a Kerr black hole, named after Roy Kerr, who found the mathematical solution in 1963. Rotating black holes are more complex than non-rotating ones. Fact 19. A rotating black hole has two event horizons, an outer and an inner one, and a region between them called the ergosphere where space-time itself is dragged around by the black hole's rotation. Inside the ergosphere, you couldn't stay still even if you wanted to. Space itself is moving. Fact 20. In principle, you could extract energy from a rotating black hole by dropping something into the ergosphere at just the right angle. The object would gain energy from the black hole's rotation and could escape, leaving the black hole with slightly less angular momentum. This is called the Penrose process. As you rest now, let yourself feel the strangeness of these objects. Black holes are places where space and time themselves behave in ways that seem impossible, where the rules we're used to no longer apply. And yet they're real, natural, following the laws of physics with perfect precision. Let that strangeness be oddly comforting. The universe is far more complex and mysterious than our everyday experience suggests. There are things in the cosmos that challenge our intuitions, that force us to expand our understanding, that remind us how much we still have to learn. You don't need to understand all of it. You don't need to visualize curved spacetime or calculate Schwarzschild radii. You can simply appreciate the mystery, the wonder, the deep strangeness of a universe that contains objects as extreme as black holes. Breathe slowly. Feel your body, solid and stable, resting on solid ground, held by ordinary, comprehensible gravity. And let your mind drift into the peaceful darkness, that same darkness that fills black holes, complete and absolute. A darkness that's also a kind of rest. Fact 21. Black holes form when massive stars die. Not all stars become black holes, only the most massive ones. Stars like our sun will never become black holes. They're not massive enough. Fact 22. Stars shine by fusing hydrogen into helium in their cores. This fusion releases energy, creating an outward pressure that balances the inward pull of gravity. As long as fusion continues, the star remains stable. Fact 23. But stars don't live forever. Eventually, they run out of hydrogen in their cores. For stars like the Sun, this marks the beginning of the end. The core contracts, the outer layers expand, and the star becomes a red giant. Fact 24. Sun-like stars will eventually shed their outer layers and leave behind a white dwarf, a dense, hot remnant about the size of Earth, but containing most of the star's original mass. White dwarfs are supported by electron degeneracy pressure, a quantum mechanical effect. Fact 25. More massive stars can fuse heavier elements. After hydrogen comes helium, then carbon, nitrogen, oxygen, neon, magnesium, silicon, and finally iron. Each stage of fusion requires higher temperatures and lasts for shorter periods. Fact 26. Iron is the end of the line. Fusing iron requires energy rather than releasing it. Once a massive star's core fills with iron, fusion stops. There's nothing left to hold up the star against gravity. Fact 27. What happens next is catastrophic. The core collapses in less than a second, falling inward at velocities approaching 70,000 kilometers per second, a significant fraction of the speed of light. This collapse releases enormous amounts of gravitational potential energy. Fact 28. The collapsing core rebounds when it reaches nuclear densities, sending a shock wave outward through the star. This shock wave, combined with intense neutrino emission, blows apart the star's outer layers in a supernova explosion, one of the most energetic events in the universe. Fact 29. A typical supernova releases more energy in a few seconds than the Sun will release in its entire 10 billion-year lifetime. For a brief period, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. Fact 30. What's left behind after the supernova depends on the mass of the collapsing core. If the core is less than about 2 to 3 solar masses, it becomes a neutron star, an incredibly dense object about 20 kilometers across, made almost entirely of neutrons. Fact 31. Neutron stars are supported by neutron degeneracy pressure, similar to how white dwarfs are supported by electron degeneracy pressure, but at much higher densities. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Fact 32. But if the collapsing core is more massive than about 2 to 3 solar masses, no known force can stop the collapse. Neutron degeneracy pressure isn't strong enough. The core continues to collapse past the neutron star stage, shrinking smaller and smaller. Fact 33. As the core collapses, its escape velocity increases. The escape velocity is the speed you'd need to leave the object's surface and overcome its gravity. As the core shrinks, this velocity increases. Fact 34. When the escape velocity reaches the speed of light, the event horizon forms. At this point, the object has become a black hole. The collapse continues inside the event horizon, but we can never observe it from outside. Fact 35. This whole process, from the moment fusion stops to the formation of a black hole, takes less than a second. One moment, there's a massive stellar core. The next moment, there's a black hole. Fact 36. The black hole that forms from a stellar collapse typically has a mass between 3 and 20 solar masses, though some can be larger. These are called stellar mass black holes, to distinguish them from the much more massive black holes found at the centers of galaxies. Fact 37. Not every massive star becomes a black hole. The exact boundary depends on the star's composition, rotation, and other factors. But generally, stars more massive than about 20 to 25 solar masses are likely to form black holes when they die. Fact 38. Some stars are so massive that they skip the supernova stage entirely. Instead of exploding, they simply collapse directly into black holes, a process called direct collapse. The outer layers fall inward and disappear behind the event horizon with barely a whisper. Fact 39. These direct collapse events are called failed supernovas. Astronomers have observed several cases where a massive star simply disappeared, becoming much dimmer but not exploding. Likely, these stars collapsed directly into black holes. Fact 40. There's another way to create black holes, by compressing matter without a stellar collapse. If you could somehow compress any amount of matter into a small enough volume, it would form a black hole. The mass doesn't have to come from a star. Fact 41. In the early universe, just after the Big Bang, Density fluctuations might have created primordial black holes. Black holes formed from the direct collapse of dense regions in the hot, early cosmos. These black holes could have any mass, from tiny to enormous. Fact 42. Tiny primordial black holes, if they exist, would be smaller than atoms but could contain the mass of a mountain. They would be incredibly difficult to detect, but might account for some of the dark matter in the universe. Fact 43. Supermassive black holes, the giants at the centers of galaxies, probably didn't form from stellar collapse. They're too massive. Instead, they might have grown from smaller black holes that merged together or from direct collapse of massive gas clouds in the early universe. Fact 44. The exact formation mechanism for supermassive black holes is still being researched. We know they exist, we can measure their masses, but we're not entirely sure how objects with millions or billions of solar masses came to exist so early in the universe's history. Fact 45. What we do know is that black holes, once formed, are incredibly stable. They can last essentially forever, slowly growing by accumulating matter or merging with other black holes, gradually evaporating through Hawking radiation over timescales that dwarf the current age of the universe. As you drift now, think about stellar death and rebirth, about how the most massive stars don't fade quietly but go out in spectacular explosions, leaving behind these strange remnants, these tears in the fabric of space-time. There's a cycle to it, beautiful in its own way. Stars are born from clouds of gas and dust. They live for millions or billions of years, shining steadily, converting hydrogen into helium and heavier elements. And then they die, returning their processed material to space, where it will eventually form new stars, new planets, new possibilities. Black holes are part of this cycle. They're not endpoints or failures, but transformations, matter taking on a new form, following gravity to its logical conclusion. And they'll continue existing long after ordinary matter has decayed, long after the last stars have burned out, patient and unchanging, following the laws of physics through eternity. Let that patience enter you now. Let the slow, inevitable processes of stellar evolution be a metaphor for your own processes, your own cycles of activity and rest. You don't need to rush. You don't need to force anything. Just like gravity, rest comes naturally when you stop resisting, when you let yourself collapse into comfort, when you surrender to the inevitable. Breathe deeply. Feel yourself becoming heavier, sinking deeper into rest. And let the darkness around you become complete, comfortable, peaceful, like the darkness inside a black hole where all complexity dissolves into simplicity, all motion into stillness. Fact 46. The event horizon is the most important feature of a black hole. It's the boundary beyond which escape becomes impossible, the point of no return. Cross the event horizon, and your fate is sealed. You will reach the singularity. There's no way back. Fact 47. From the outside, the event horizon looks like a perfectly black sphere. No light comes from inside it, so it appears completely dark against the background of space. The only way to see it is by its effects on surrounding matter and light. Fact 48. The event horizon is not a physical barrier. There's no wall or membrane. It's simply the boundary where the escape velocity equals the speed of light. Inside this boundary, you'd need to travel faster than light to escape, which is impossible. Fact 49. If you were falling toward a black hole, you wouldn't feel anything special as you crossed the event horizon. There's no jolt, no sensation, nothing to mark the moment. From your perspective, space looks normal. You just keep falling. Fact 50. But from the perspective of someone watching from far away, something strange happens. As you approach the event horizon, they see you moving slower and slower. Time dilation becomes extreme. They never actually see you cross the horizon. Fact 51. This is because light from you takes longer and longer to reach the distant observer as you get closer to the horizon. The light is redshifted, losing energy, becoming dimmer and dimmer. Eventually, you fade from view, frozen forever just above the event horizon from the outside perspective. Fact 52. This creates a paradox. From your perspective, you cross the horizon in finite time. From an outside perspective, you never cross. Both perspectives are valid. This is relativity. Different observers can have different but equally correct descriptions of the same event. Fact 53. Inside the event horizon, space and time switch roles in a sense. Outside, you can move freely in space but are forced to move forward in time. Inside, you're forced to move toward the singularity, which is in your future, but time becomes somewhat negotiable. Fact 54. This doesn't mean you can time travel inside a black hole. It means that the singularity is not a place, but a moment in time, an inevitable future event that you'll reach just as inevitably as you reach next Tuesday outside the black hole. Fact 55. The journey from the event horizon to the singularity takes finite time from your perspective. For a stellar mass black hole, it might be a fraction of a second. For a supermassive black hole, it could be hours or even days. Fact 56. As you fall toward the singularity, tidal forces become important. The difference in gravitational pull between your head and your feet, or between your left side and your right side, creates stretching and squeezing forces. Fact 57. These tidal forces increase as you get closer to the singularity. Eventually, they become strong enough to tear you apart, stretching you like spaghetti in a process astrophysicists call spaghettification. It's a technical term that appears in serious scientific papers. Fact 58. For a stellar mass black hole, spaghettification would begin before you even crossed the event horizon. The tidal forces are so strong that you'd be torn apart well before reaching the point of no return. You'd never actually experience crossing the horizon consciously. Fact 59. But for a supermassive black hole, the tidal forces at the event horizon are much weaker because the horizon is so much farther from the singularity. You could cross the horizon intact, surviving for hours inside before tidal forces eventually destroyed you. Fact 60. In principle, you could orbit inside the event horizon for a while if you had a rocket powerful enough, though you'd still inevitably fall to the singularity. Inside the horizon, all paths lead to the center. You can delay but not prevent reaching the singularity. Fact 61. The event horizon has some strange properties. For instance, its surface area always increases or stays the same, never decreases. When black holes merge, the total surface area of their event horizons increases. Material falling in increases the surface area. Fact 62. This property of event horizons led physicist Jacob Bekenstein to propose that black holes have entropy proportional to their surface area. Entropy is a measure of disorder or information, and Bekenstein suggested that black holes store information on their event horizons. Fact 63. Stephen Hawking initially disagreed with this idea, but later realized Bekenstein was right and even calculated the exact temperature of black holes. Black holes have temperature, which means they emit radiation. This radiation is now called Hawking radiation. Fact 64. Hawking radiation is produced by quantum effects at the event horizon. Virtual particle pairs appear near the horizon, and occasionally one particle falls in while the other escapes. The escaping particle carries away energy, causing the black hole to slowly lose mass. Fact 65. For stellar mass and supermassive black holes, Hawking radiation is incredibly weak, far weaker than the cosmic microwave background. These black holes are effectively gaining mass from their surroundings much faster than they lose it through Hawking radiation. Fact 66. But given enough time, if the universe continues to expand and cool, eventually Hawking radiation will dominate. Black holes will begin to evaporate, slowly losing mass, shrinking, becoming hotter as they shrink, until finally they disappear in a burst of radiation. Fact 67. The time it takes for a black hole to evaporate through Hawking radiation is proportional to the cube of its mass. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate. A supermassive black hole could take 10 to the power of 100 years or more. Fact 68. These timescales are so long they're almost incomprehensible. The universe is currently only 13.8 billion years old, which is 1.38 times 10 to the power of 10 years. The evaporation time for even a small black hole is trillions of times longer than the current age of the universe. Fact 69. When a black hole finally evaporates completely, what happens to the information that fell in? Does it disappear, violating the laws of quantum mechanics? Or is it somehow encoded in the Hawking radiation? This is called the black hole information paradox. Fact 70. Stephen Hawking originally argued that information is destroyed in black holes. Later, he changed his mind and accepted that information is probably preserved, though we don't fully understand how. This remains one of the deepest puzzles in theoretical physics. Fact 71. The event horizon is also where the force of gravity becomes formally infinite according to some calculations, though what this really means is unclear. It's another indication that our theories break down in the extreme environments near black holes. Fact 72. Despite their extreme nature, event horizons are actually quite fragile in a sense. They're not made of anything physical, but are just geometric features of spacetime. Yet they have real effects, preventing light from escaping, storing information, producing radiation. Fact 73. Some theories propose that event horizons might be replaced by something else, like firewalls of high-energy radiation. According to this idea, you'd be incinerated as you approach the horizon, not by the black hole itself, but by quantum effects. Fact 74. Other theories suggest that black holes might not have event horizons at all, or that the horizon is some kind of membrane made of fundamental particles. These ideas are speculative, attempts to resolve paradoxes and unify quantum mechanics with gravity. Fact 75. For now, the classical picture of event horizons remains our best description. They're boundaries in space-time, not physical objects, defined purely by geometry and gravity, serving as one-way membranes through which matter and energy can enter but never leave. As you rest now, think about boundaries, about points of no return, about the moment when one state transitions to another and cannot be reversed. The event horizon is the universe's ultimate one-way street, the clearest example of irreversibility in nature. But boundaries like this exist in your life too, less dramatic but equally real. Every moment you live through becomes the past, irretrievable. Every choice you make closes off other possibilities. Every breath you take is exhaled and gone forever. This isn't sad or frightening, but simply the nature of time, the way causality works, the structure of reality. You move forward through time, always in one direction, crossing countless small event horizons that separate past from present, present from future. And right now, you're approaching another boundary, the transition from waking to sleeping, from consciousness to dreams, from the activity of day to the rest of night. This boundary is softer than an event horizon, more permeable. You'll cross it and return in the morning. But for now, let yourself approach it without resistance. Let the boundary come closer. Let consciousness begin to fade. Let the point of no return approach and arrive and be crossed without fear or hesitation. Sleep is waiting on the other side, deep and peaceful and restorative. Just let go. Just fall. Just cross the boundary into sleep, into the darkness, into the quiet rest that awaits beyond the threshold of waking. You're almost there. Almost across. Almost asleep. Fact 76. At the center of almost every large galaxy, including our own Milky Way, sits a supermassive black hole. These objects contain millions to billions of solar masses, far more massive than any star. Fact 77. The supermassive black hole at the center of the Milky Way is called Sagittarius A*, pronounced Sagittarius A star. It has a mass of about 4 million suns, and it's located about 26,000 light-years from Earth. Fact 78. Despite its enormous mass, Sagittarius A is relatively quiet. It's not currently eating much material, so it doesn't emit much radiation. It's essentially sleeping, a dormant giant at the heart of our galaxy. Fact 79. We can't see Sagittarius A directly with optical telescopes because it's hidden behind dense clouds of gas and dust in the galactic center. But we can observe it using radio waves and X-rays, which penetrate the dust. Fact 80. The best evidence for Sagittarius A's existence comes from watching stars orbit around it. Astronomers have tracked dozens of stars in the galactic center for decades, measuring their orbits with exquisite precision. Fact 81. One star, called S2 or S0-2, has a particularly tight orbit around Sagittarius A star. It completes one orbit every 16 years, reaching speeds of up to 7,650 kilometers per second at its closest approach, about 2.5% the speed of light. Fact 82. By tracking S2's orbit and the orbits of other nearby stars, astronomers calculated that there must be 4 million solar masses in a very small region at the galactic center. The only object that dense and compact is a supermassive black hole. Fact 83. In 2022, astronomers released the first image of Sagittarius A*, created using the Event Horizon Telescope, a global network of radio dishes working together as one Earth-sized telescope. The image shows a bright ring surrounding a dark shadow, the black hole's event horizon. Fact 84. The Event Horizon Telescope actually images the photon sphere, not the event horizon itself. The photon sphere is a region just outside the event horizon where light can orbit the black hole. It creates a bright ring in images, with the event horizon forming the dark center. Fact 85. Creating an image of Sagittarius A was incredibly difficult. The black hole's event horizon is tiny from Earth's perspective, about 52 microarcseconds across. That's like seeing a donut on the moon from Earth. Fact 86. The image of Sagittarius A looks similar to the earlier image of M87, the supermassive black hole at the center of the galaxy, M87. Both show bright rings surrounding dark centers, confirming that black holes look the way Einstein's theory predicts. Fact 87. M87 is much more massive than Sagittarius A, containing about 6.5 billion solar masses. It's one of the most massive black holes ever measured, sitting at the center of a giant elliptical galaxy 55 million light-years away. Fact 88. M87 is actively feeding. Unlike Sagittarius A, matter falling into M87 forms an accretion disk, a swirling disk of superheated gas that shines brilliantly in many wavelengths. Some of this material is funneled into jets that shoot outward at near light speed. Fact 89. The jets from M87* extend for about 5,000 light-years, visible in radio and optical images. These jets are created by magnetic fields in the accretion disk, which somehow channel some of the infalling material into narrow beams traveling at 99% the speed of light or faster. Fact 90. How do jets form? This is still an area of active research. The basic idea is that magnetic fields get twisted by the rotating accretion disk and the black hole's rotation, creating powerful magnetic funnels that accelerate particles to extreme speeds. Fact 91. Not all supermassive black holes produce jets. Those that do are called active galactic nuclei or quasars, depending on how bright they are and how we observe them. A quasar is just a supermassive black hole feeding very actively, shining brighter than its entire host galaxy. Fact 92. Quasars were more common in the early universe when galaxies had more gas available to feed their central black holes. Today, most supermassive black holes are relatively quiet, having consumed most of the nearby gas. Fact 93. The relationship between a galaxy and its central black hole is intimate. The black hole's mass correlates strongly with the mass of the galaxy's central bulge. More massive galaxies have more massive black holes, suggesting they co-evolve. Fact 94. This relationship is surprising because the black hole's mass is typically only about 0.1% of the galaxy's bulge mass. How does something so small compared to the galaxy influence the galaxy's evolution? Fact 95. The answer seems to be feedback. When the black hole feeds actively, it releases enormous amounts of energy through radiation and jets. This energy heats gas in the galaxy, preventing it from cooling and forming new stars, effectively regulating the galaxy's growth. Fact 96. Computer simulations show that without this feedback from supermassive black holes, galaxies would form too many stars and become much more massive than observed. The black holes act as thermostats, controlling star formation. Fact 97. How did supermassive black holes form in the first place? This remains uncertain. They might have grown from smaller black holes that merged together, or they might have formed directly from the collapse of massive gas clouds in the early universe. Fact 98. Either way, supermassive black holes appear to have formed very early. We've found quasars less than 1 billion years after the Big Bang, meaning supermassive black holes existed when the universe was less than 10% its current age. Fact 99. These early supermassive black holes challenge our understanding of black hole growth. To reach billions of solar masses in less than a billion years requires extremely rapid growth, faster than standard models predict. Fact 100. One possibility is that some black holes formed much more massive than stellar collapse would produce, perhaps containing thousands or tens of thousands of solar masses at birth. These seed black holes could then grow to supermassive sizes more quickly. Fact 101. When galaxies merge, their supermassive black holes eventually merge too. This creates gravitational waves, ripples in spacetime that carry energy away from the system. Future gravitational wave detectors might observe these mergers directly. Fact 102. The merger of two supermassive black holes would create gravitational waves with wavelengths of light years, far too long for current detectors like LIGO. But proposed space-based detectors like LISA could detect these signals. Fact 103. Supermassive black hole mergers might happen more frequently than we think. Many galaxies show signs of having two active nuclei, suggesting they contain two supermassive black holes that haven't merged yet. Fact 104. The final moments before two supermassive black holes merge would be spectacular. As they spiral together, they'd create gravitational waves that shake the entire galaxy, potentially disrupting star orbits and triggering bursts of star formation. Fact 105. After merging, the new black hole might receive a kick from asymmetric gravitational wave emission, giving it a velocity of hundreds or even thousands of kilometers per second. This could eject the black hole from the galaxy entirely, though this is probably rare. As you drift deeper now, think about these giants at the hearts of galaxies, these objects containing the mass of millions or billions of suns compressed into regions smaller than our solar system. They're the heaviest objects in the universe, the ultimate expressions of gravity's power. And yet they're peaceful most of the time, sitting quietly at galactic centers, patiently waiting for gas to fall in, regulating star formation through their occasional meals, shaping the galaxies around them through subtle influences we're only beginning to understand. There's something majestic about them, something almost serene despite their extreme nature. They're not violent monsters, but natural features of the cosmic landscape, as much a part of galaxies as stars and gas, contributing to the ecology of the cosmos in essential ways. Let that quiet majesty enter your rest. Let yourself feel small but connected, a tiny part of a universe that contains such wonders, such extremes, such strange beauty. You're made of atoms forged in stars, living in a galaxy centered on a supermassive black hole, resting on a planet that orbits an ordinary star. Everything is connected. Everything is part of the same cosmic story. And right now, your part is to rest, to sleep, to let consciousness fade into the quiet darkness that fills the universe between the stars, the same darkness that fills the hearts of black holes. Breathe softly. Let your body sink completely into stillness. And let yourself be held by the gravity of sleep, pulled gently down into rest, crossing the threshold into dreams, into the deep darkness where peace and restoration await. Fact 106. Black holes do not suck things in like cosmic vacuum cleaners. This is perhaps the most common misconception. Black holes have strong gravity, but so do stars of equivalent mass. If the sun became a black hole right now, Earth's orbit wouldn't change at all. Fact 107. Gravity is gravity, whether it comes from a star or a black hole. The key difference is that with a black hole, you can get much closer to the center of mass. If you got as close to a black hole as you're currently standing from Earth's center, the gravity would be much stronger. Fact 108. But from a distance, a black hole's gravity is no stronger than the object that formed it. A black hole with the sun's mass would pull on Earth exactly as hard as the sun does now. We'd orbit normally, just in darkness because no light would be coming from the central object. Fact 109. Black holes don't wander around galaxies eating everything in their path. They move through space following ordinary orbital mechanics, just like stars. Most black holes sit peacefully in their orbits, occasionally encountering gas or stars, but not actively seeking them out. Fact 110. You cannot use a black hole as a portal to another universe or time travel device. Science fiction loves this idea, but it doesn't work with our understanding of physics. Going through a black hole means being destroyed by tidal forces and hitting the singularity. Fact 111. Some theoretical solutions to Einstein's equations do suggest connections between different regions of spacetime through black holes, called wormholes. But these solutions require exotic matter with negative energy, which probably doesn't exist, and they're likely unstable anyway. Fact 112. Black holes don't live forever in the traditional sense, but they last an incredibly long time. Through Hawking radiation, they slowly evaporate, but this process is so slow that even the smallest black holes would outlast most stars by factors of trillions. Fact 113. Black holes don't destroy information in the way people sometimes imagine. The black hole information paradox is complex and still debated, but the leading view is that information is preserved somehow, perhaps encoded in the Hawking radiation or on the event horizon. Fact 114. You cannot see inside a black hole, and not just because it's dark inside. The event horizon prevents information from escaping, so there's no way to observe what's happening inside. The interior is fundamentally cut off from the exterior universe. Fact 115. This creates an interesting philosophical question. Does it even make sense to talk about what's inside a black hole if we can never observe it? Some physicists argue that science should only address observable phenomena. Fact 116. Black holes don't get infinitely massive. There are theoretical upper limits based on how much mass can be in a given region before various instabilities set in. The largest black holes we've observed contain about 60 billion solar masses. Fact 117. Primordial black holes, if they exist, don't have minimum sizes based on stellar collapse. They could be any mass, from tiny, less than an atom, to enormous. But we haven't found definitive evidence for primordial black holes yet. Fact 118. Black holes do not lead to white holes that expel matter in another part of the universe. White holes are mathematical solutions to Einstein's equations, but they're probably not physical. They'd require extremely special initial conditions that don't occur naturally. Fact 119. Black holes can't be created in particle accelerators on Earth. The energies needed are far beyond anything we can produce. Theoretical micro-black holes that might form in high-energy collisions would evaporate instantly through Hawking radiation, producing harmless particles. Fact 120. The fear that the Large Hadron Collider could create dangerous black holes was based on misunderstanding. Even if micro-black holes formed, they'd be incredibly tiny, evaporating in 10 to the power of negative 23 seconds or less, far too quickly to interact with surrounding matter. As you rest now, let these clarifications ease any unconscious fears you might have about black holes. They're strange objects, yes, but they're not monsters or threats to everyday life. They're natural features of the universe, governed by understandable laws, predictable in their behavior. The universe is full of extremes, of objects and phenomena that push the boundaries of what's possible within the laws of physics. Black holes are among the most extreme, but they're also among the most well understood, at least in their basic properties. You can rest easy knowing that black holes, despite their fearsome reputation, are just doing what massive objects do, creating gravity wells, following geodesics through spacetime, obeying the same rules that govern planets and stars and galaxies. Let that understanding bring peace. The universe, for all its strangeness, is consistent. The laws of physics apply everywhere, to everything. And those laws, while they allow for extreme phenomena like black holes, also create the stability and predictability that makes planets like Earth possible, that allows life to exist and flourish. You're safe on your planet, in your galaxy, in a universe that contains black holes but keeps them at safe distances, that creates these extreme objects but doesn't let them dominate or destroy everything else. The cosmos balances extremes with stability, chaos with order, darkness with light. Breathe deeply. Let go of any lingering concerns or misconceptions, and let yourself sink into the comfortable darkness of approaching sleep, a darkness that's nothing like the extreme darkness of a black hole, but is instead warm and gentle and welcoming, a place of rest and renewal. Fact 121. Black holes emit no light themselves, so we can't see them directly in most cases. Instead, we observe their effects on surrounding matter and light. It's like seeing wind by watching trees bend, or detecting a planet by its gravitational influence on its star. Fact 122. The first black hole to be widely accepted was Cygnus X, 1. Discovered in 1964. It's a strong X-ray source in the constellation Cygnus, about 6,000 light-years from Earth. Fact 123. Cygnus X. 1 is in a binary system with a blue supergiant star. The black hole pulls gas from the supergiant, and this gas forms an accretion disk that heats up to millions of degrees, emitting X-rays we can detect from Earth. Fact 124. By observing the motion of the supergiant star, astronomers determined that its unseen companion must have at least 15 solar masses. The only object that massive and compact is a black hole. This was confirmed through decades of observations. Fact 125. X-ray binaries, systems where a black hole or neutron star orbits with a normal star, are the easiest stellar mass black holes to detect because the infalling gas shines brightly in X-rays. Fact 126. We've now identified dozens of stellar mass black holes in X-ray binaries, with masses ranging from about 5 to 20 solar masses. These observations confirm that stellar collapse can indeed create black holes. Fact 127. Another way to detect black holes is through gravitational lensing. When a black hole passes between us and a distant star, the black hole's gravity bends the starlight, creating a characteristic brightening pattern. Fact 128. Gravitational microlensing surveys have detected isolated black holes this way, though it's rare. The events are brief, lasting weeks or months, as the black hole's motion carries it across our line of sight to the background star. Fact 129. In 2015, scientists achieved something revolutionary. They directly detected gravitational waves from two merging black holes using the LIGO detectors. This was the first direct observation of gravitational waves and definitive proof that black hole mergers occur. Fact 130. The two black holes that LIGO detected had masses of 36 and 29 solar masses. They spiraled together and merged, creating a final black hole of 62 solar masses. The missing 3 solar masses were converted into gravitational wave energy, radiated away in less than a second. Fact 131. Since that first detection, LIGO and other gravitational wave detectors have observed dozens of black hole mergers. We now have a whole catalog of these events, revealing that black hole mergers are relatively common in the universe. Fact 132. Gravitational wave astronomy has revealed black holes with unexpected properties. Some are more massive than we thought stellar collapse could produce, suggesting either they form differently or our understanding of stellar evolution needs refinement. Fact 133. One of the most exciting detections was GW190521, which produced a black hole of 142 solar masses. This falls in what was thought to be a forbidden range, too massive to form from stellar collapse, but too small to be a supermassive black hole. Fact 134. This intermediate mass black hole might have formed from the merger of two smaller black holes, which themselves formed from stellar collapse. Or it might indicate new formation mechanisms we haven't considered. Fact 135. The 2019 image of M87*S Event Horizon, captured by the Event Horizon Telescope, was another breakthrough. For the first time, we could actually see the shadow of a black hole's event horizon against the glow of its accretion disk. Fact 136. Creating that image required coordinating 8 radio telescope arrays across the globe, synchronized using atomic clocks, effectively creating an Earth-sized telescope. The data processing took 2 years and sophisticated algorithms to turn radio signals into a visual image. Fact 137. The success of the Event Horizon Telescope showed that our understanding of black holes is fundamentally correct. The image matched predictions from Einstein's general relativity, confirming that black holes really do have event horizons and behave as the theory predicts. Fact 138. We've also observed black holes through their effects on stellar orbits, particularly near Sagittarius A* at the center of the Milky Way. Stars orbiting the galactic center move at incredible speeds, their orbits shaped by the invisible black hole's gravity. Fact 139. By tracking these stellar orbits over decades, astronomers have precisely measured Sagittarius A*''s mass, about 4 million solar masses, and location, within a few light minutes of the dynamical center of the Milky Way. Fact 140. Some black holes are detected through jets and outflows. Active galactic nuclei and quasars create powerful jets visible in radio waves, and these jets can extend for millions of light years, making them easy to spot despite the black hole itself being invisible. Fact 141. The brightest objects in the universe are quasars, supermassive black holes actively feeding on gas. Some shine with the light of trillions of stars, visible from across the universe, their brightness revealing the presence of black holes billions of light years away. Fact 142. We're now entering an era where black hole astronomy is becoming routine. New telescopes and detectors are coming online that will allow us to observe hundreds or thousands of black holes in various ways, building a comprehensive picture of these objects. Fact 143. Future gravitational wave detectors, like LISA in space, will detect merging supermassive black holes, opening a new window on these giants. We'll be able to observe black holes that are currently invisible, studying them through the space-time ripples they create. Fact 144. Advanced computer simulations now model black holes and their environments in exquisite detail, helping us interpret observations and predict what we might see with future instruments. The agreement between simulations and observations continues to improve. Fact 145. Every new observation confirms what Einstein's theory predicted over a century ago. Black holes exist, they behave as the equations describe, and they're real, natural objects following the laws of physics like everything else in the universe. As you rest now, think about how human ingenuity revealed these invisible objects. Black holes don't emit light, don't leave obvious traces, exist as pure distortions in space-time. And yet we found them, studied them, imaged them, confirmed their existence beyond any doubt. This is the power of science, of observation, of mathematics, of patient work by thousands of people over decades. We took Einstein's abstract equations and turned them into concrete predictions, then built instruments sensitive enough to test those predictions, and found that reality matches the mathematics. There's something beautiful in that, something almost poetic. The universe is comprehensible. Even its most extreme phenomena can be understood through reason and observation. Even objects as strange as black holes yield their secrets to patient inquiry. Let that thought bring comfort. The universe, despite containing extremes beyond everyday experience, is not arbitrary or unknowable. It follows rules, patterns, mathematical descriptions that human minds can grasp and test and confirm. You're part of a species that can look up at the night sky and understand what's out there, that can detect objects invisible to eyes, that can peer into the hearts of galaxies and watch space-time itself ripple. That's remarkable, worthy of wonder, a source of quiet pride. And right now, you can rest in that knowledge, in the understanding that the universe is both stranger and more comprehensible than common sense suggests. You don't need to understand all the details. You can simply appreciate the mystery and the methods we've developed to unravel it. Breathe slowly. Feel yourself sinking deeper into sleep. And let the darkness around you be comfortable, knowing that even the deepest darkness of black holes has been illuminated by human understanding, mapped and measured and understood through science's careful light. Fact 146. Despite their extreme nature, black holes are actually quite safe for us. The nearest known black hole is about 1,000 light-years away, far too distant to have any effect on Earth. We're in no danger from black holes. Fact 147. Even if a black hole were to pass through our solar system, which is incredibly unlikely, it would have to pass very close to Earth to be dangerous. From even a few astronomical units away, its gravity would be no stronger than a star of equivalent mass. Fact 148. The most likely ways black holes might affect us are indirect, through their influence on galaxy formation and evolution, through their role in recycling matter and energy, through their contribution to the overall structure and behavior of the cosmos. Fact 149. Black holes might even be necessary for life. By regulating star formation in galaxies, they help create the long-term stability needed for civilizations to arise. Without supermassive black holes at galactic centers, galaxies might form stars too quickly and exhaust their gas supplies. Fact 150. In the far future, long after the sun has died and Earth has been destroyed, black holes will be among the last objects remaining in the universe. They'll persist for googolls of years, slowly evaporating through Hawking radiation, the final lights going out in a cold, dark cosmos. As you drift into the final moments before sleep, let these facts about black holes settle into your mind like stars settling into their orbits. Black holes are strange, yes, extreme beyond everyday comprehension, but also natural, beautiful in their own way, essential parts of the cosmic machinery. They're reminders that the universe is far more interesting than the small corner we inhabit, that beyond Earth and the sun and the familiar night sky, there are wonders that challenge our understanding and expand our imagination. You've journeyed tonight through the physics of black holes, from their formation in dying stars to their role at the centers of galaxies, from the mathematics of event horizons to the observations that proved they exist. You've separated myth from reality and glimpsed both the strangeness and the comprehensibility of these cosmic extremes. Now it's time to rest. Time to let these thoughts fade into the background as sleep approaches. Time to cross your own event horizon, the boundary between waking and sleeping, between consciousness and dreams. Let yourself fall. Let gravity pull you down into rest. Let the darkness embrace you, not the extreme darkness of a black hole, but the gentle, welcoming darkness of sleep where consciousness dissolves and the body repairs itself. You're safe here, on this planet, in this galaxy, in this universe that contains both extreme phenomena and stable, nurturing environments. The black holes will continue their patient existence, billions of light years away, while you rest and dream and wake refreshed to another day. Breathe your last conscious breaths of the night. Feel your body completely relaxed, supported by the bed, held by Earth's gravity. And let yourself cross the threshold, fall through the event horizon of sleep, into the singularity of deep rest where time stops and only peace remains. Good night. Rest well, and let the peaceful darkness of sleep hold you safely through the night, as safe as you've always been, as safe as you'll continue to be, in a universe that contains both wonders and safety, both extremes and stability, both black holes in the depths of space and comfortable beds in quiet rooms where tired people can finally rest.